Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. So in the last lecture, we were discussing the parametric estimation technique where the parametric form of the densities were known, where the parameters which defines that density function are unknown. So we have used the maximum likelihood estimation technique to estimate those parameters. So let us solve one problem where we have the given density function as this, and we have to estimate the optimal parameter of theta. For that, the likelihood will be maximized. So here we have this problem. So now here we have given parameter set D is x1, x2 and xn, and which is drawn independently according to p of x given theta. Okay, so here this distribution is given to us. So we can compute p of d theta equal to, we have to multiply all the probabilities associated with the data samples given parameter theta. So here we have the expression like this. Okay, so we can put the density expression as theta e the power minus theta x when x is greater than equal to 0. Okay, so now we have to compute the log likelihood of theta. So we have to take the ln of this term. So ln of p of d theta equal to, so when we will compute it, the multiplication will turn to summation, and these two terms are also in the multiplication, so it will be ln theta minus exponential, and ln will be cancelled out, so minus theta xk. Okay, so this is our likelihood. So here we have to maximize this term with respect to theta. So what we have to do, we have to take the derivative of L theta with respect to theta, and then we will equate to 0. So here gradient of theta L theta will be dl theta d theta, and this term will be equal to, so derivative of ln theta will be 1 by theta minus xk. Okay, and here k equal to 1 to n, and we will equate this term to 0 so that we can get the solution for theta, and that will be our estimated theta for which L theta will be maximum. So here summation 1 by theta k equal to 1 to n minus summation xk, where k equal to 1 to n equal to 0, then n by theta equal to summation xk, k equal to 1 to n. So here we can write that theta, which is the estimated value of theta, equal to 1 by n summation xk, k equal to 1 to n. So here the denominator is basically the mean of the sample values. So we can write estimated theta is 1 by n. So this is our solution. Okay. Now let us discuss the non-parametric parameter estimation technique. So we have already seen that for statistical pattern classification, density functions are to be known for each class, as we have seen in the parametric estimation technique. There we have some information about the density function. Now let us discuss the non-parametric parameter estimation technique. So we have seen that for statistical pattern classification, density function are to be known for each class, as we have seen in the Bayesian classifier. And the type of density functions such as normal density function or Poisson density function are to be known to estimate the parameters of densities, and that approach is called the parametric estimation that we studied in the last class. In most of the real problems, even the type of the density functions of interest are unknown. So in the parametric estimation technique, we assume that the parametric form of the density functions were known, however the parameters were unknown. But in this case, it may be possible that we don't have any information about the density function. Okay. So in that case, we will use the data samples, okay, and we will look at the histograms, scatter plot, and tables of the data samples, and that will suggest that a particular type of class density may be used or some arbitrary density can be used. Okay, so if the arbitrary density function is used, then that can be estimated from the data samples using non-parametric method, because whatever the data we will have, okay, then suppose we plot the histogram of the data samples, then from the histogram we can say that which type of the distribution the data sample is following. Okay, however, in most of the classical parametric densities are unimodal, whereas many practical problems involves multimodal. So unimodal means if you will have the distribution something like this, that means only one mode we have. Okay, so this shape is kind of one mode. In many practical applications, we may have the multi modes. Okay, so in this case, here, if we will assume that our distribution is Gaussian, but maybe the parameters are unknown, we can apply the parametric estimation technique. But in case of multimodal case, here we cannot consider that our distribution is Gaussian or it is any other known distributions, because this distribution is unknown, which is multimodal density functions. So in that case, non-parametric method can be used with arbitrary distributions and without the assumption that forms of the underlying densities are known. That means we will not consider any information regarding the density function. So under non-parametric method, there are different approaches for continuous variable and discrete variable. So in real life, we have the continuous variable. So we can quantize it to get the discrete variable, or we can use as is, okay, as it is, so that the variable will be continuous. Okay. So if we apply the parameter estimation technique on the discrete data, then we have to use the histogram method that will estimate our probability mass function, because the probability mass function is nothing but the probability density function for discrete feature vectors. If we have continuous feature vectors, then we can have the estimated probability, which is given by k divided by n divided by v. Here k is the number of samples in the volume v, and n is the total number of samples. So if we consider that volume size is fixed but k is varying, in that case we have to apply the Parsons window technique. Okay, the Parsons window consider this condition, and if we vary the window, that means if we will vary the volume and we will fix the number of samples in that volume, then that approach is called the k nearest neighbor approach. So here we have three approaches to estimate the non-parametric parameter estimation techniques. Okay. So let us discuss the histogram based method to estimate the density function, and this approach is non-parametric parameter estimation technique. So a very simple method is to partition the space into a number of equally sized cells or bin and compute a histogram. So whatever the data samples we will have, we will compute the minimum and maximum value of the data samples, whatever the values we have. Okay, and then we will partition the space in equally spaced bins. Okay, and that will be our histogram. So we will see one problem, that how we can compute the histogram and how we can compute the probability density function to make the decision. So here we can estimate the density at a point x, which is given by this expression, okay, where n is the total number of samples and k is the number of samples in the bin that includes x. Okay, so that means that bin is basically the volume. Okay, and v is the volume of that cell. That means cell and bin is same thing here. So we will find the number of samples in the volume v. So if we are dealing with one-dimensional feature vector, then v will be the width of the bin, and if we are dealing with the two-dimensional feature vector, then volume will be our area. Okay, so here to choose the bin size, we have a thumb rule that the number of bins to be equal to square root of the number of samples. So how many bins we have to consider to compute the histogram? That will be the square root of the total number of samples. So this is the thumb rule to compute the number of bins. So let us solve a problem using histogram based density estimation. So let us solve a problem using histogram based technique to estimate the class conditional densities. So here this problem is about the classification of samples using histograms and the Bayesian decision rule. So what this problem says, use the following data to classify a sample with x equal to 7.5 given that the prior probability of class A and class B is 0.5 and the following data are values of feature X for 60 randomly chosen samples from class A and class B. So here we have to take the decision about this data samples which is x equal to 7.5. So here we have to make the decision whether this x equal to 7.5 belongs to class A or class B, where we have given the prior probabilities but we don't have the class conditional probability, and that class conditional probability can be estimated using these data samples. That means from these data samples we need to estimate the class conditional densities using histogram method. So let us compute the histogram of these data samples. So to compute the histogram, first we should know that what is the bin size. So from these data samples you can observe that the minimum value of the data sample is 0.8 and the maximum value is 9.86. So here basically the value is from, we can say that roughly it is from 0 to 10. Okay, so we can divide the feature space into equally spaced bin size. So let us consider the bin size is 1. So we will have bin size 1. So let us consider 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So here on the y-axis is the frequency of occurrence of data samples in this bin. Okay, that means in different bins. So here we will count the number of samples which falls in these bins. So let us consider the first bin is from 0 to 1, where 1 is included in this bin. So let us count. So here we have 1, 2, 3, 4. So here 4 number of data samples which falls in this bin. So let us denote it 4, 8, 12, 16. So here 4. So 4 number of data samples in this bin. Now the bin 1 to 2. So here we can count 1, 2, 3, 4, 5, 6. Okay. So the 6 number of data samples in this bin. Similarly, we can count the number of data samples in bin from 2 to 3. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here we have 12 number of data samples in this bin. Okay. So we can count the number of data samples between bin 3 to 4. So it is 1, 2, 3, 4, 5, 6, 7. So it is 7. Okay. Then next, between 4 to 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So here we have 16 number of data samples. The number of samples in this range, it will be 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. Between 6 to 7, 1, 2, 3, 4, 5. So here it is 5. Then we will count the number of samples between 7, 8. So it is 2. Okay, and in this bin we don't have any samples. So this is the histogram of the data samples belongs to class A. Similarly, we can find the histogram for the data samples belongs to class B. So we have chosen the bin size 1. Okay. So in the bin, in the first bin, we don't have any samples. In the second bin as well, we don't have any samples. In third bin also, we don't have any samples. But in the bin, so number of samples between 3 and 4, we have 1, 2, 2 samples. So number of samples between 4, 5, 1, 2, 3, 4, 5, 6. Number of samples between 5, 6, 1, 2, 3, 4, 5, 6, 7. So this is 2, 6, 7. Number of samples between 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. So it will be 17. Now the number of samples between 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here 14 number of samples in this bin. The number of samples between 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here 11 samples. And between 9, 10, 1, 2, 3. Okay. So this is the histogram of the data samples which belongs to class B. So this is basically the histogram. So we need to convert it to the probability density function, and how we can convert it, we have to divide each bin with the total number of samples, and here we have total number of samples and equal to 60, and here also n equal to 60. So we have to divide 4 divided by 60, then it will give us the probability densities x given a. Okay, and here we can compute the probability density function, and it will be p of x b. Okay, so it is 4, 8, 12, 16. So we have this probability will be 4 divided by 60. Okay, so in this way we can compute all. So this will be 6 by 60, this will be 12 by 60, then we will have 7 by 60, then 16 by 60, then 8 by 60, then 5 by 60, then 2 by 60. So this is the basically the probability density function. Okay, similarly we can compute the probability density function of class B. So here 1, 2, 3 will be 0 by 60, so it will be 0. Okay, so here this will be 2 by 60, then 6 by 60, then 7 by 60, then 17 by 60, then 14 by 60, then 11 by 60, then this is 3, so it will be 3 by 60. Okay, and we have given x equal to 7.5. Okay, we need to classify this. Okay, and prior probabilities are same, so we can compute p of omega 1 given x equal to 7.5 equal to, so our decision will not depend on the prior probability, it will totally depend on the class conditional probability. So here the class conditional probability, that means p of x given 7.5 for class 1, so here 7.5 will fall in this bin. Okay, and here the probability is 2 by 60, so this is 2 by 60. So we can compute the posterior probability p omega 2 given x equal to 7.5. Here also the same prior probability, so we can omit the prior probability, so we need to consider only the class conditional probability. So p of x given 7.5 for class 2. Okay, so here 7.5 will fall in this range. Okay, so here, and the probability is 14 by 60. Okay, so here P of omega 2 x equal to 7.5 is greater than P of omega 2 given x equal to 7.5. So our decision will be in the class omega 2. That means x will be classified to class omega 2. Okay. So here x will be classified to class omega 2. So the histograms are not restricted to one-dimensional densities as we have seen. We can also compute for the any dimension. Okay, that means we can apply the histogram based the probability density estimation technique, okay, for any number of dimensions. So if we will deal with the two-dimensional feature space, then we have to compute the probability density function in the two-dimensional space. So we will have the two feature values, feature components x and y, and it will be approximated by dividing both x and y into intervals and determining the number of samples that fall within each rectangular histogram being with dimension del x and del y. Suppose we have the two-dimensional feature space. There we have to divide the each feature component axis in equal beings, and there we will count the number of samples that fall within that rectangle, because del x and del y will create one rectangle, and in that rectangle we have to compute the number of samples, and that will be our probability estimate. And if it will be volume, then we have to divide the three feature component axes. Okay. So however, the histogram technique will become impractical for space for high dimensional space. If it will very high dimensional space, then maybe this approach will not be very accurate. Okay. So whenever we will apply this approach, we have to check the dimensionality of the feature vector as well. Okay. So this much for this lecture. I hope I am clear to you. If you have any doubt, you can ask in the comment section.